So today, well actually just since I don't know everyone in the room, I'm Bill Hirsch. I'm the chair of the department, the director of the educational program. Today is the third of 3 days where we have our summer interns present their work, how they spent their summer vacation, although maybe it wasn't vacation. But at least the ones I worked with had a good time. And I understand we also have some other folks in the room, which is this is the week of our data analytics short course. So I welcome some of you who I probably know by name, but maybe not by face. In any case, it's good to have a nice big audience here. So the usual procedure for these is to have the student's mentor present them. So I'm going to turn it over here to Dr. Chang, who will introduce our first speaker.
Bill, thanks. Well, I am Michael Chang, and I have the pleasure of introducing Jessica Wallace. Jessie. And if you guys don't know, Jessie is going to be a senior at the University of Oregon, and she's studying biology. And she actually had an interesting bit of history that when she was in high school, she worked as an EPIC trainer at St. Vincent's. And I learned all about EHRs and workflow from that experience. So the group that I work with a couple people who you guys will know, Michelle Rybar and Tom Yackel. And we've been doing some projects involving EHRs, workflow, and modeling. And Jessie worked on part of this project that she'll talk about. And she's done a really great job here. She's been fun to work with. And she's integrated really, really well with the team. So Jessie, why don't you go ahead and talk about all this stuff. Thanks.
Thank you. So as Dr. Chang said, I'm Jessie Wallace, and I was his intern this summer. And I'm going to be talking to you today about EHR time demands for ophthalmology documentation. So I'm going to start today by discussing, giving you a brief background history of electronic health records and how that ties into the project I worked on this summer, which was a 2-part analysis of documentation in ophthalmology. I'll discuss my methods for data collection and analysis, as well as the results I obtained from my project. And finally, we'll conclude with why all of this matters. So electronic health records provide many benefits that are simply not possible with traditional paper records. The ability to share patient data between multiple providers is great and improves the comprehensive care for the patient. On a larger scale, EHRs allow us to extract large amounts of data in an efficient way that can be used to populate registries and be used in all types of research. This can then not only lead to better treatment for future patients, but also can help us to build more efficient IT tools such as EHRs that can be used for physicians in the future. Some of the earliest EHRs date back to as early as the 1960s. However, their implementation in hospitals didn't start getting significant attention until around the early 2000s. OHSU implemented its EHR system EPIC in 2006. And was very successful. However, this wasn't common in all transitions. Many transitions were met with resistance from physicians who did not want to move away from the traditional paper records for fear of it not, being what they were used to and possibly taking up more of their time. In 2009, the federal government stepped in and passed the HITECH Act in 2009, which the purpose was to promote the meaningful use and adoption of these EHR systems. So starting in 2011, the federal government used Medicare and Medicaid incentive payments to reward physicians and hospitals that chose to adopt these EHR systems. And starting this year, they will begin enacting penalties for professionals and hospitals that are not using them. Over this time period in ophthalmology, EHRs have seen an increase in use from 12% in 2007 to 34% in 2012, and we can estimate today that that is somewhere in the realm of 50 to 60%. But if these are such great tools and there are incentives for using them, why aren't these numbers higher? So ophthalmology, like other specialties, has its tends to have a unique workflow and specific documenting techniques that are not always compatible with EHR systems that can generally be built for unspecialized primary care providers. Ophthalmology clinics tend to have a complex workflow, which result from a high patient volume, as well as patients seeing multiple healthcare staff during one visit. On top of that, some patients come in for dilated eye exams, and dilation of the eyes can add an additional 30 minutes to a patient visit. These factors that go into these complex workflows tend to lead to inefficiencies in these clinics that result in long patient wait times, and some doctors fear that the use of EHRs will only make this worse. For documenting in ophthalmology, using these type of templates that I have up here were a common practice before the use of EHRs, and while there are similar templates in EHR systems, they tend to not be as easy to use or allow the same freedom that paper templates do. Also, many patients have their eyes imaged during their visits, and these are a big part of making proper diagnosis. However, these images are not easily transferable to the EHR systems that we're currently using. Some other concerns with implementing EHRs in ophthalmology clinics include a fear of lower patient volume, as well as doctors having to spend more time focusing on a computer than a patient in the exam room. On top of that, more time documenting outside of work. So the purpose of the project that I was working on was to hopefully provide some evidence for how physicians were interacting with these EHR systems to either back up or discredit these concerns. So as I mentioned before, my project was a two-part analysis. The first part was a time motion data analysis, and this part of the project was meant to answer the question, what percentage of exam time do physicians spend documenting during a typical encounter? And then the second part was an audit log timestamp data analysis that was meant to determine how much time physicians spend documenting per patient, as well as when and where they do this documentation. Finally, I wanted to bring these two analyses together to give like a snapshot of how ophthalmologists interact with these EHR systems. So the first part of my project was this time motion data analysis. And for this part, I helped perform manual observations of 5 providers from the Casey Eye Institute. And the purpose of these observations was to determine how exactly a physician was spending its time with a patient. To do this, we separated provider activity into 3 broad categories, which were documenting, talking, and examining. And during these observations, I would shadow a provider and timestamp when they would switch from one activity to another. And then at the end of the day, I would go back through and calculate the times they spent in each activity per patient. Since I joined this project a little bit later, I had to be trained to do these paired observations. And what this entailed was me and Sarah, who's here, would do observations together, essentially, and would independently document, what the provider was doing, and then calculate our time separately and compare them to see if we were having any significant differences in times. What we found was that there were no significant differences and that we were essentially equivalent. So from that point on, I performed the rest of the observations by myself. Some of the tools that I used included the numbers application on the iPad. This is what we use for our time stamping device, as well as Microsoft Excel for all time calculations and data analysis and representation. So this graph here represents the results that I obtained from these observations. As you can see, we have the 5 different providers, and then in parentheses, you can see the average encounter time, so the average length of time they would spend with one patient. Then you can see that these light blue bars represent the percentage documenting, the dark blue represent percentage of time was spent talking with the patient, and finally these gray bars represent the percentage of time that was spent examining. One thing to note, there was a range of about 21% from provider C to 35% provider A of the time spent documenting, and in provider A, the time spent documenting trumped all other activities. On average, we found that providers were spending about 25% of their time documenting per one encounter. While this isn't a majority of their time spent with the patient, with already short exam times, which on average was about 11.5 minutes, This is still a significant amount of time, and it's important to try and figure out if there's a way to cut this down. So some of the limitations of this, this part of the analysis, determining when one activity started and another ended could be difficult. There is often some transition time, as well as, you know, if a patient or if a physician was multitasking and then switched to just doing one activity, it could be difficult to decide, you know, when that change really happened. Also, since there was only 3 categories, it could be difficult to place certain activities in one of those 3 categories. And in that case, I really just had to use my best judgment and try to be as consistent as possible. We also felt that the paired observations helped kind of remind us that although there would be some variance, they probably did not have a significant effect on our results. Another limitation was that the Numbers app was not the best time-stamping device. It was a little bit slow in the sense that you had to input a lot of information before being able to timestamp. And this was difficult when the physician was switching back and forth between different activities. However, it still got the job done. So the second part of this analysis was using EHR audit log data. And EHRs, while they hold a lot of patient information, also hold a lot of information about who's using them, when, where. EHRs, they actually record a timestamp for every entry into their system, which create these audit logs that I've been talking about. So that is a lot of information, and we were able to kind of query these audit logs to find the times from our 5 providers during the 2014 year that they spent, you know, entering data into these EHR systems. And we also used some data from the Cognos database, which just essentially gives information about patient check-in, check-out times, which we use to kind of determine, you know, when a physician was maybe in an exam and when they were outside of that. So another member of our team, Michelle Rybar, who's not here today, came up with an R script that allowed us to combine these audit log and Cognos data sets. And from that, we were able to determine the average time that physicians spent documenting per patient, as well as when and where this was performed. We also worked to try and validate these audit log times with the time motion data that we received. And the main purpose for this was that you know, there's a lot more information that we can use from the audit logs, and the time motion data studies were pretty time consuming. And if we could get times from these audit logs that matched our, what we felt were more accurate observation times, then we could be using these timestamps on their own, and they would be accurate. So this table is an example of the data we got from one of the physicians we observed. As you can see, it gives the time spent documenting in an exam room during business hours, which, but outside the exam room, and then during non-business hours. And for the purpose of this project, business hours was defined as Monday through Friday, 8 to 5. So as you can see, this provider spent about 3 minutes per exam documenting. There's another 4 minutes outside of the exam room, but still within the business hours documenting, and then another minute on top of that documenting outside of their normal business hours, for a total of 8.6 minutes documenting per patient. While these numbers might not mean much standing alone, if we think about one hypothetical clinic day, which we can say is about 40 patients on average, this results in 124 minutes documenting in exam, 172 minutes documenting outside of the exam but still in business hours, and then another 44 minutes outside of business hours, for a total of 344 minutes, or almost 6 hours of documenting per 1 day of clinics. So that is a significant amount of time, I would say, and although it's hard to compare with, you know, with no baseline, having these numbers now is important because we can work to maybe bring them down with newer and more efficient EHRs. So another chart that we were able to produce from our data was this kind of more comprehensive graph that shows, this is just for one provider, all the hours of the day, and then what percentage of their total documentation was done in each hour. So as you can see, the yellow in the bars represents the in-exam time. The light blue is non-exam business hours, and the darker gray was non-business hours. And so these are interesting to compare between providers because it really gives you an idea of the different strategies that they employ to get their documenting done in a timely manner. And our goal is to kind of be able to create these graphs and also the table that I showed you previously for a number of providers to give an idea of, you know, the range of how this documenting gets done. So as I mentioned before, we wanted to try and validate these EHR timestamps. And the main purpose for this was really to, you know, prove that they were accurate enough to stand alone. And if we could do that, then we wouldn't have to be doing these kind of time-consuming observations and could rely on the vast amounts of information that's already present in EHRs. So what we did is we were able to compare the observed documentation times in exam with the in-exam documentation times we got from our audit logs. And as you can see, they are not exactly the same. However, we feel that they are similar enough, and we can work towards, you know, making them more similar, which will come with, you know, deciding how we want to use that R script that I mentioned earlier to extract the data that we need. So some limitations to this part of the study. The biggest issue was that the audit log times counted timestamps in minutes and not seconds. So this posed two significant issues that revolved around determining the length of 1-minute timestamps. So when a provider is documenting on multiple patients at the same time, which tends to happen more outside of the exam room and outside of business hours, there can be multiple timestamps within 1 minute, but they can be for different patients. So for example, if there were 8 timestamps in 1 minute and 5 of those were for one patient and 3 of those were for another, what we ended up doing was weighting these. So we would give 3/8 of a minute to that patient and then another 5/8 to the other patient. And then also we had an issue with standalone minutes, which were more of a problem for the in-exam room documenting. And what this means is that there was just a 1-minute timestamp, kind of, you know, not near other timestamps that could mean that the provider was documenting for that whole minute, but it could also mean that they clicked one button and it could have lasted a matter of seconds, the document that they were doing. So what we did is we decided to count these 1-minute timestamps as 30 seconds. We felt that this would eliminate some of the variance in the times that it could potentially be. Another limitation was trying to get this, use the R script as like a one-size-fits-all method. All these providers have different workflows and somewhat different business hours, which was significant when working with the R code. Determining, we wanted to use the same business hours, and we wanted to use like check-in and check-out times from the Cognos data to determine when a physician was in exam versus outside of exam. However, this wasn't always the most accurate representation for each provider, so we were still working to kind of find a model that fits all. So why does all this matter? We wanted to provide some concrete evidence for how physicians are spending their time documenting in the EHR, and we felt that this was important because it could be used to advocate in the future for more efficient and specialty-specific EHRs. Also, the validation of EHR timestamps we think could be a really valuable tool in the future, because if we can find a way to prove that these timestamps and data are accurate, it can be used for vast amounts of other research in a similar field. And finally, I want to say thank you to the project team I worked with, Michael Chang, Sarah, and Michelle Rebar, who is not here, as well as Dr. Thomas Yackel, who assisted on the project. Thanks to all the providers that allowed me to observe them and hang around in their clinic. And then also to the departments, the faculty that have been really helpful over this internship, and all the interns. And special thanks to Emily for sitting next to me all summer. And thank you for listening to my presentation.
Thanks. Very interesting results. If your numbers are correct, you're talking about 6 hours a day documenting. There was a paper published about a year ago that caused a lot of unease because primary care physicians were found in, I don't know if they use the same methods as you guys did, but to spend about 30% of their time sitting in front of a computer, which alarmed a lot of people, although in reality physicians, even back in the paper days, spent plenty of time with records. But if your 6 hours are correct, I mean, you're talking, 50, 60, 70% of their time documenting. And then that leads to a more micro question, which is it possible that when they're in the exam room and they have the documentation open, that they're moving back and forth between examining and documenting so that they're really not spending that full minute documenting?
Yeah, so that's a great question. So the in-exam room stuff, I didn't get a chance to touch on this, but we had kind of this hierarchy system for, humans inherently multitask. So if someone was documenting and talking at the same time, we did count that as documenting. Same for examining and talking. We kind of just said that everything was going to trump talking. But in reality, a lot of physicians, I feel like, are very good now at being able to document and interact with their patient at the same time. So, yeah, a lot of that time does come from the in-exam documenting, but it might not be as bad as, just staring at a computer while the patient's sitting there. I think, especially now that it's been around, at least at OHSU for a long time, physicians are good at really integrating it into the exam room.
Have you checked back with these clinicians and shown them your data, and how do they feel about it?
We have not. We actually are still going to perform, I think, a couple more observations before the summer. So this data is still a little bit preliminary, but there are a couple physicians who do seem interested in the project, and I think they would love to see some of these, images that we've created, and I think it'd probably be fine to show it to them. Hopefully it will be in a paper someday.
What are some of the things that you might suggest as solutions to decreasing the workload?
Well, I think it's interesting to do this study in a specialty like ophthalmology that does have its, unique issues. I think the biggest thing is just going to be able to build EHRs that are more efficient, and that's easier said than done, but also making them more specialty specific. I think the biggest problems come with, right now they're kind of built for more of a broad use, which doesn't really integrate well with a lot of other specialties. So I think the biggest thing is getting them more specific.
So how specific do you think this is to OHSU and KCI Institute compared to other ophthalmology practices?
I'm not sure. I think OHSU in general has done a really good job with training employees and integrating the EHR system, so it might not even be as big of an issue as it is other places, and then there are still clinics who have yet to make the transition. But I think regardless of how well it works, it's more of an issue with the technology and finding a way, for it to really be useful for the physicians that are using it. So definitely something to think about everywhere, but I think OHSU is probably, handling it a little bit better. Okay, yeah, thanks.
One of my ophthalmologist is one of your subjects. I guess I can ask her the next time I see her. No, she's too busy. Oops, I just gave her away, I think. Good. Okay. Our second speaker since I was her mentor, I will be introducing Adrienne Beebe, who has been spending the summer. Unfortunately, we still have a few weeks with her, working on a project in the department that some of you know about. And it's actually pertinent to the course that's going on this week, which is that last year we received a couple grants from NIH to develop curricular materials in the Big Data to Knowledge program. And Adrienne has been working on various aspects of that. She comes to us, she just received her bachelor's degree from, it's on the tip of my...
Whitman College.
Whitman College. I don't know why I forgot that. Anyways, Whitman College, and where she majored in math and economics. I remembered that. She's been with us this summer and is going to talk about the work she's done in this Open Educational Resources project.
All right, thank you. Yeah, as Dr. Hirsch said, I worked on the Big Data to Knowledge Open Educational Resources project. And so the Big Data to Knowledge, or BD2K, is an initiative through the National Institutes of Health to, quote, enable biomedical research as a digital research enterprise, facilitate discovery and support new knowledge, and maximize community engagement. What this means is that right now we're really good at producing data and storing data, but there aren't a lot of resources for actually using data, especially in a biomedical setting. And so what our project aims to do is to create open access materials that anyone can download, to use, learn from, or manipulate and teach. The target audience is grad students, undergrad students, and also senior professionals who are just starting to learn how to use big data. The ONC, the Office of the National Coordinator for Health IT, in the past released similar materials for data science, but as it's a quickly changing field, it's time to update those. So the timeline of our project is to do 2 cycles over the next 3 years of a needs assessment, development and dissemination of materials, and evaluation. And right now we are obviously after July, before November. We've released some modules, and I'll get to modules in a moment. And so right now we're just working on the first round of development. And so the project leaders identified 32 modules, and each module is a topic that all surround clinical and biomedical research, challenges of data, semantic web and ontologies, data modeling, and of course, big data. And so I came into this project after a couple modules had already been developed, and my goal for the summer is to find data sets, preferably big data sets, and use them to create supplemental exercises and materials to go along with the modules. So I started with a handful of things to look into, and that quickly became a lot of rabbit holes to delve into. And you find a lot of different sources of data out there. But then how do you decide which ones could be useful in this setting? And so I developed kind of an informal, honestly somewhat subjective set of assessment. And so the 4 V's of big data, which kind of identify something as big data versus just regular data, are volume, velocity, variety, and veracity. Volume, is it big? Velocity, is it being quickly generated, so not just a stagnant data set from 5 years ago that's not changed. Variety, are there different data types? Are there different kinds of variables? And veracity, how reliable is the source? And then format. If I find a data set, can I actually look at it? Is it in a file type that I can download? Or is it just summary statistics that are locked in a PDF file that I can't do anything with and that no one can really learn from in the context of big data? Documentation. Is the data well documented? Are the variables actually named and described? Rights. Since our project is all about open educational resources, we want it to be something public that we can share and that other people can use. We have had a little bit of trouble. Sometimes the website will say, yeah, this data is open for anyone to use, but you have to apply for it, and you can only be a researcher, and then you can't actually share it. So we're not sure, we haven't quite decided how we're going to handle that, if we're just going to provide links, etc. And topic. This is about biomedical, clinical, translational research are kind of our big things. And so if the data set wasn't really relevant to medicine, healthcare, etc., didn't really look at it. So getting into data documentation, if I find a data set, I want to be able to document it in a way that the rest of the team can use it, especially after I'm gone after the summer. And so this is just a little snapshot of a couple data sets that I found. They have to do with patient discharges in New York hospitals. The first one has to do with heart failure cases, and the second has to do with newborns. And so I have a spreadsheet that basically rates the 4 V's of big data. And so for these data sets, volume, pretty good volume, a couple 100,000 observations. Maybe not big data, but bigger than something that had only a couple 100 observations. Velocity, it's okay. It's released yearly, pretty regular, even though it's not necessarily what we call streaming data, constantly being produced. It's not terrible. Variety, about 30 variables, which is okay. Veracity, this is from the New York State Health Department, so probably pretty good, reliable source. Data management, I don't expect you to read all of this, but I'm just going to tell you about metadata. If you're not familiar with metadata, it's data about data. So our data is the data set, and the data about that data is the title, who created it, when it was created, etc. Dublin Core is a great system of using metadata. It's about 15 categories, which are listed up here. And it's pretty easy to use. It's pretty easy to find most of the categories. And it's easy for someone else to come into and read. And so there's different kinds of standards. Some of them have like 50 fields. We decided on Dublin Core because it's pretty widely used and accepted. Data dictionaries. Not exactly the same as metadata. This gets down into the different variables in the data set. So this is going back to the same data set that I talked about earlier, heart failure and New York hospital admissions. And each name is a variable. There's a bunch more. This is just a little snapshot. And it's a great way to document the definition, the data type of that variable, and different values it can take on. For example, the age group. Age could mean anything. If someone who's never seen this data before just sees the variable age, it could be a continuous integer, it could be a discrete integer, but in this case, it's a categorical variable, and it takes on, and it's basically a string, so that means it's a phrase. And the different values it can take on are 0 to 17, 18 to 29, etc. So this is just a really good way to consistently and thoroughly organize a data set. And like I said earlier, another big part of what I'm doing this summer is developing exercises to go along with the modules. And so right now where I am in that part of the process is essentially brainstorming and working with the principal investigators on the modules that they've developed to create exercises. I'm not an expert in the modules that they've developed, so I can only so far read through what they've created and start thinking of things on my own. And so some examples. For Module 6, which is clinical data and standards related to big data, a possible exercise would be to have a large set of hospital discharge data, like clinical data, and you can query it, so basically filter it based on ICD-9 codes, standards. And ICD-9 codes, if you're not familiar, are codes that have to do with diagnosis, et cetera, of cases. Another possible exercise would be in Module 8, Public Health and Big Data, is to have a data set from social media, like Twitter posts. There's a cool website called Topsy that has all tweets ever, or since 2006. And you can use that for what's called digital epidemiology. So if you've heard of Google Flu Trends, basically that's Google looking through what Google searches have been done to try and predict how many flu cases there are pretty much at a given time. And so we could try to replicate something like that with Twitter, for example. And so the project so far, at the beginning of the summer, this is what our website looked like. Honestly, it was just a place to store what's already been done. It's not super pretty, but with the help of our instructional designer, it's gone from this to this. So it looks like an actual, like a well-designed website. And so internet willing, I can show it to you. Internet is willing. So, well-designed website. We have the goals right up front and how it's being developed. We can go over here. We have the topics. And so far on this website, just the first one has been released. biomedical, clinical, and translational research. But we also see all the other 31 topics that are under development. And we can view the topic content, maybe. Aha. And here you can download the slides, the audio, and all other resources so that you can use it wherever you are, and you can even modify it for your own uses. And now the lectures, we use a tool called Articulate, and that combines PowerPoint slides with audio, so you have an online lecture. And so this is what it would look like. And what you can't hear, because I turned the sound off, is Bill's voice talking about biomedical, clinical, and translational research. Draft 1 of this presentation was just showing this and listening to Bill talk. And so now this might be a little boring, just sitting there, reading what's on a PowerPoint slide, listening to someone talk who you can't even see, have never met. But Articulate has this cool tool called Interactions. And what that is it's a way to engage with whoever's listening or watching your lecture. And we can use it to, and the specific example that I'm about to show you, we use it to ease cognitive load. So basically what that means is instead of just having a block of text on a page, we break that up so that it's much more presentable to the user. And so this would be a before we used an interaction. It's just a lot of text on a page. But then here is an after. This is called a folder interaction. So for this case study, let me go back. We have a patient, Jessica, has a disease. It's gotten worse. It's expensive. And the parents don't know what's going on. So this is just a lot. It doesn't really this slide doesn't tell a story. But now, here's a little bit of background information about Jessica. Here's her diagnosis. Here's what's going on. And then here's the treatment. So it's just a way to break up the same information on the original slide to a way that's much easier to see. And so the future work, I've got about 3 more weeks here. And what I'm going to do is hopefully learn more about access and analysis of big data. Something that honestly the project is currently lacking and what's been developed is once you get your hands on a big data set, like a really big data set, how do you actually use it? So far the project has a lot of good theory about data management and ideas about it, but say you're not a computer programmer and you find a file that's about 1 gigabyte, which this one is about 2 million lines of code. Microsoft Excel can only open, or rows of data, rather. Microsoft Excel can only open about 1 million lines. And so then what happens when you get to the 1000 Genomes project that has 200 terabytes of data? And your computer maybe only has like half a terabyte of storage. So I hope to work with Dr. Shannon McQueenie about how to actually get that big data working. And also I'm going to contribute to a couple of the modules. Module 13 is version control and identifiers. I'm currently learning how to use Git and GitHub, which are ways to basically manage a project, especially with a team, using version control. So for example, if 2 people are working on the same file, and then you try and upload that file back to the group, it basically manages who sees what and what the most updated version is. And also Module 15, which is Data and Tools Landscape. And so where to find and access data, that's basically what I've been doing all summer. So I feel confident that I'll be able to contribute to that one. So yes, that's what I am going to do for the rest of the summer. And I'd like to thank my mentor, Dr. Bill Hirsch, and all the other PIs on this project, Nicole Vasilevsky, Bjorn Peterson, Dr. Melissa Handel, Dr. Shannon McQueenie, and everyone who's contributed to the BD2K OER project, and of course, to the fantastic summer interns that I worked with this summer. Thank you. Questions? Yeah, it is available. This one? Yeah. I have the URL down here, Skynet, which is BD2K. Yeah, it is public. Anyone can look at it. And our next benchmark is in November, which is when we hope to have all of the modules and exercises, at least in their first stage of development, to be public on the website. Yeah.
Curious, does this website have an annotation of tools or analytical techniques that have been applied to different sets of big data?
I don't think it does right now. Yeah, we're still working on actually getting the modules out, and we do have a whole lot that are still under development about more computational and analytical side of things. But not yet. All right. Thanks. Probably.
I guess I'll use my old slides then. Oh, thank you. No. Oh, okay. Thank you. All right.
All right, fine. Okay. I see. Cool. Well, my name is Stephen Wu, and I'm an adjunct assistant professor here at DMICE. And about a year ago, I got an R01 grant to work on information retrieval from electronic health records to do cohort identification. And so Andrew has come in and is working on the core methodological research, the core interests of this research grant. So I've been very fortunate to be his mentor. Andrew is a rising senior at Portland State and studying computer science. He is a very, very talented programmer. He, I think, got interested in it from the gaming industry, I think, but has found something more interesting and meaningful in biomedical informatics. It's been a pleasure to work with him, and I think he's made more progress than I expected. With 3 weeks left, he's made more progress than I expected him to make all summer. So I really appreciate the time with him. I'll leave it to you, Andrew.
Okay, thank you, Dr. Wu. So as Dr. Wu mentioned, I'm going to be talking today about facilitating cohort discovery through use of layered language models. So your first question is probably going to be, what the heck is cohort discovery? So cohort discovery is identifying patients with a certain set of attributes. So for instance, it can range from stuff like demographic data to age, gender, to stuff like this patient has a certain set of conditions, or this patient has undergone certain forms of treatment. So here are several examples of this. So as you can see here, both of these examples have treatments, so PET, MRIs, CTs, or as well as conditions, so back pain, for example, or cancer. And so you have these cohorts you want to discover. So what you do is you send a search request to, you have a big repository of electronic health records that you can ask to return data from. So which electronic health records match what I'm looking for? So you search this, and okay, so that sounds like that works, right? Except it doesn't quite. So the naive way of searching, which is how a lot of search engines work, is you go by keywords. So you start with something like heart attack, that separates into the words heart and attack, and you ask the database, okay, find me documents that have these two words in them. And so one example where one word matching gives you a point of 1, a score of 1, would be, okay, so you have this right here, suffering a heart attack, and that causes further complications. So this is a score of 2. It has 2 words matching. Okay, so clearly this works. This has a score greater than 0, so it thinks it matches. But consider this, where you have a knife attack right above the heart. That's also a score of 2. It has the 2 words matching, attack and heart, except it's not quite a heart attack, although it might. lead to your heart dying, sure. But using this scoring model, for instance, it would still think, it gives a score of 2, it thinks it's equally relevant as a document that explicitly says heart attack in it. And then, as a further example, consider myocardial infarction is a different way of saying heart attack. Suffers from a myocardial infarction. This would get a score of 0 because it doesn't have the word heart attack in it. And this is wrong because it's still talking about heart attack. And for something more subtle, like severe chest pain due to a coronary thrombosis, this is symptoms, not heart attack itself, but it still suggests heart attack. So you would still want to return the result in your search. And this would also get a search score of 0 because it doesn't have the words in it. So the solution to this is actually to use semantics to address the shortcomings here. So for instance, with the limitation where you can't find synonyms, you would normalize the data. So you would normalize heart attack and myocardial infarction along with all of its other synonyms into a common term. So for instance, you can use concept UIDs that all of it matches this heart attack and myocardial infarction both match this concept UID specifically. Or you can use other codes, for instance, ICD-9 codes. You can use, I think we also use SNOMED or something. And another major limitation is you lose relational data. So what that means is, for instance, you're looking for patients with a lesion on the hypothalamus. And you're looking for lesion hypothalamus. Okay, they have, but for instance, if you were to have lesion on, or lesion proximal to the hypothalamus, for instance, that would also match. It would have both of the major words. You have like lesion, hypothalamus, but it doesn't have that actual relation, which is on top of, not next to. So you would also be searching for relations, such as you have a noun that the location of that noun is on top of this other noun. But so I'm going to actually use this term a lot subsequently. So a layer is basically a semantic type, which is a concept UID relation. Or actually, these two aren't the only types of semantics possible. You can have sentences, you can have parts of speech, along with a variety of other semantic types. So the major limitation here is you still can't only search a single layer. So if you only search a single layer, you lose the benefits of having the other layers. For instance, using the examples I gave beforehand, if you go with a keyword search, you miss out on synonyms and you miss out on relationships. If you go with a relationship search, you're only looking for the relation. So if you're looking at location of, so you have this noun is located on another noun. You're looking for that. Lesion on the hypothalamus matches, but so does fracture on your I don't know, femur. Because both of these, the location, you're looking for the location of relation, and you have a condition location of other object. And then as a further example, if you're looking for normalized terms, so where you convert all the synonyms into one common term, you lose granularity. So you may wish, you may have symptoms and both. So for instance, with the heart attack example, you have heart attack and then you have chest pain and coronary thrombosis. Both of these match heart attack, but you may wish to give more weight to something that says, explicitly says this patient has heart attack as opposed to just describing the symptoms. So the solution to this is actually to just search for multiple layers at once. And rather than searching for keywords, so rather than searching for this specific term within a given semantic type, we look for multiple combinations of these. So we look for a token would just be, we have this word within the semantic type. We can have windows, which is we have an artifact, which is a token window or phrase that's listed here. An artifact that contains a set of other artifacts. So for example, this sentence, we want to look for this sentence that contains word 1, word 2, word 5, right? Or we can have a phrase, which is basically two artifacts next to each other, let's say, and within a given distance of each other. So we say, I want this term right next to this term. I want heart right followed immediately by attack. I don't want it in any other order. I don't want any words in between them. So, and then beyond that, we also want to give each document a score, right? So when you ask a search engine for something, you get a list of results, and you want the list of results, you want the most relevant thing to be first up, because you don't want to scroll through 50 pages of things to find what you're looking for, right? So this is an example scoring model, and you may be asking, why am I showing you this equation? Because obviously you don't know what any of these terms mean yet. So TF here means term frequency, which is actually how often the artifact we are looking for appears in our document. CF means collection frequency, so how often the artifact we are looking for appears within our entire document index. So the important thing to note here is that we actually compared the two together. So if we have a term that doesn't occur often within our document, but occurs very often within the entire document index, so our other documents all contain a lot of this term, we may wish to score differently as opposed to if we have a term that occurs a lot within this document but doesn't occur at all within the document index as a whole, because in that case, in the latter case, it would be considered pretty significant. And so mu here in this case would just be the weight between well, it's a form of weighing the two together, weighing the local document frequency as opposed to collection level frequency. So I've talked so far about the concepts behind what I'm working on. So I'm actually going to talk about what I actually worked on this summer, which is actually implementing all of this within the search index. So in order to cover this, I'm actually going to cover how searching works. So you start with a basic text query, which then gets converted into a layered query, in a sense, which basically I want to look for this window of a sentence within that contains this word. And then that gets sent to a document index, which is basically a big collection of all of your documents. So all of your documents, your health records in this case, right? And then that document index gets you back a ranked list of results. So so what we use as a document index. So I'm actually going to start with the third box here, document index. What we actually use as a document index is called Elasticsearch, which is an inverted index. What that means is, rather than searching through all 5 million of your documents, word for each term, you store, okay, so word 1, word 1 is contained within documents 1, 3, 5, 7. So obviously you wouldn't want to look through 50 million words each search. So instead, this mapping allows you to get better performance. Another thing that gets stored is the term positions, which is actually rather important. So it says this word starts at position 1 within this document. This other word starts at position 3. And I mean, that's important because if you're using something like phrases, you have to know how far they are between each other. So, okay, so Elasticsearch supports this, but it also has major limitations. So it doesn't actually support multi-layered searching per se. So it doesn't understand the concept of layers and overlap. What that means is it will always increment each position by 1. So sentence 1, sentence 2, sentence 1 will have position 1, sentence 2 will have position 2. But for example, sentence 1 may contain 5 basic words. Sentence 2 might contain 7. And so sentence 1, you would want to start at position 1. And sentence 2, you would want to start at position 6, right? Because 1, 2, 3, 4, 5, and then sentence 2 starts. So it cannot support a token in one layer spanning multiple tokens in a different layer, basically. And then the other major limitation is that it can't support multiple tokens at the same place. So for instance, chest pain is a symptom of heart attack, right? But it can also be a symptom of a variety of other things, like, I don't know, lung cancer. Let's go with that. So it can have multiple concepts within that same location, and Elasticsearch doesn't understand that. So in order to support this, support what we actually want to do, we had to change the way documents are indexed. And to do this, we first determined the base layer. So typically, we use just the plain text of a document, so English words. And then after that, for all the different semantic types, we first we store the given terms, so tokens with a given position. So their actual position, their starting location compared to the base layer. So this token starts at position 1. This token starts at word 6 of our base layer. And then we also store token length. So this token extends for 6 words in our base layer. So we covered indexing now, and I'm going to move on to scoring. So after we put the documents into an index, we actually need to be able to change the way that it returns matches. So term frequency for anything that isn't basically, I want this word in this layer, is actually completely off in Elasticsearch. So we had to fix that. And actually, Elasticsearch doesn't even calculate collection frequencies, which, as you may have noticed before, is actually pretty important in our scoring model. And so, and it doesn't even use the formula we actually want to use. So the biggest problem actually is that Elasticsearch really does not want to let us change these things. So our solution to this was actually to write our own version of our own query, basically, that supports matching our artifacts. So we manually define within each of these artifacts, I have this word and this word. I want you to find the positions and compare them. And then we have to aggregate the frequencies correctly as well. So we do this through a 2-pass system. The first pass, we calculate document frequencies. And then at the same time, we also sum all of the respective frequencies into a big collection frequency. And then on our second pass through, we actually score the documents with the collection frequencies and the document frequencies. And so this sounds fine, it works, right? Biggest problem here is that it's actually, we have 10 million documents in the OHSU database. So if we were to actually take 10 milliseconds to do each of these things, this would take 28 hours, and you're going to get a bunch of pissed off researchers, basically. So, and we have to go through this entire thing for 2 operations. When we search things, we have to go through the entire thing twice, as I outlined beforehand. And actually, when we index things, because we're actually putting documents inside the database itself, we actually have to go through this as well, right? And we have to change each of these documents individually and actually convert them into a format that can be searched. So performance is actually really, really important in this case. And we actually solved this problem by changing a few algorithms to make them run faster, as well as parallelization, so that we can process multiple documents at once, basically. The second biggest problem is extensibility. So unfortunately, I'm unable to convince OHSU to hire me for the rest of my life. So I actually have to stay here, and I can't stay here and change things to fit exactly what is needed. So we had to ensure that the software we wrote is easily adaptable to our needs without having to rewrite everything, because that would be a waste of work, right? So we have to be able to support changing what specific semantic layers are stored within the index easily without changing any code. So we accomplish that using configuration files. And then within our queries themselves, we have to define new artifact types. So if we want to go beyond just phrases or tokens or sentences, we have to be able to define that while still allowing them to be compatible with our existing stuff. And we also have to support easily changing the formula, because the model I actually showed you earlier is not the only model that's possible. So, so I've covered what we've finished so far. So I'm actually going to cover what we're working on in the future, as well as, well, right now, I guess. So I covered the latter half of the earlier search pipeline. So now I'm going to cover query formulation, which is what we're working on. Query formulation is basically the conversion of a plain text query to a layered query that we can use to return results. And to do that, we actually, you may have noticed that there was a mu parameter earlier in the model that basically defines a weight. We don't know the value of that model, or that weight. So what we are planning on doing is we're planning on using an experimental value. and then submitting that to a TREC database. So what that is the TREC index has a set of predetermined golden standard results. So we already know if I send in this query, I want these results back. So, so we send that in with our layered query, and we compare our results to see, okay, so what documents do I have that actually match what I want? And then we repeat. We change our query model, we change our weights, and then we see, okay, does this work better? If this works better, we keep repeating up until a certain threshold is met. And then we send that threshold, or the weight that we determined to be optimal, per se, to the OHSU data, because it's a significantly larger data set. It takes longer. So we send that to OHSU data, and then we compare with results from a relevance assessment to determine how accurate it is to what we actually want. So I would like to thank Dr. Wu for being my mentor, this department for actually giving me the opportunity to be here, as well as my fellow interns. And that concludes my presentation. So thank you.
I'm scribbling, aren't I? Oh, what date is it? It says 27, right?